There are several experimental facts we have difficulty explaining using the free electron model. These are the positive Hall coefficients that we see occasionally, the temperature dependence of the conductivity of a semiconductor, photoconductivity, etc. So there are several experimental findings. Now, to account for these, we have to include a non-zero periodic potential in the Schrodinger equation for an electron in the crystal, which is basically stemming from the ion cores, the presence of these periodic ion cores. Now, we have seen one model, basically Kronig-Penney model, that takes into account this periodic potential. So this model suggested that if we use these delta function potentials for this to simplify the problem, if we use delta functions, periodic delta functions to account for these potential wells that the electrons are traveling in, we find that we must have basically energy gaps at the Brilliant zone boundaries. So that's what we have found using Kronig-Penney model. Now, so this potential, the periodic potential in the crystal leads to has several consequences. One is that it leads to a band structure in the crystal, and number two is that we must have energy gaps at the Brilliant zone boundaries in K-space. These are due to the Bragg reflections of electron waves that is creating standing wave solutions at the zone boundaries. In order to find these waves, basically in order to find the solution, we have to use this periodic potential, which is periodic in the direct lattice translation vector capital R. So V of R is equal to V of R plus capital R. So it's periodic, therefore we can express it just like the electron concentration that we did in X-ray diffraction. We can express it as a Fourier series summed over the reciprocal lattice vectors. So V of R is sum over GVG e to the IG dot R. Remember, this was basically defining our reciprocal lattice vector. So e to the IG dot capital R must be equal to 1. So if we have V of R plus capital R, we obtain this, and that's basically defining the reciprocal lattice vector. Now, what is the form of the wave function that is due to electrons that are subject to this periodic potential? Well, first of all, we have one observation that the probability of finding an electron at a position R must be periodic. So therefore, since the probability distribution is given by the magnitude of the wave function square, so absolute value of psi square must be periodic, because that's the observable quantity that's associated with the electron. So it must have periodicity of the lattice. So we can say that if we apply a translation operator on a wave function psi, so that it becomes psi x plus a, that is equal to the eigenvalue t times psi of x. So that's one way to express this. And the most general form of psi satisfying the condition that psi square must be periodic is u of x e to the ax, where a is a complex number and u of x is a function that is periodic with period of the lattice constant a. So u of x plus a is equal to u of x. So we can write this in the form of a plane wave multiplied with a modulating function u of x. So psi of x is equal to u of x e to the ikx, or in 3D, u of r position vector e to the ik dot r. So it's basically a plane wave that is modulated by this function u of r. So this state function is known as the Bloch function. So as you can see, it has the form of a traveling wave, which signifies that the electron propagates through the crystal like a free particle. However, there is a modulation on the wave, so that the amplitude oscillates from one cell to another. So as we can see here, we have a modulation. And you may have noticed here that I have the the maxima at the that's coinciding with the ion cores here, or if we continue, the minima will coincide with the ion cores here. So the probability of finding the electron in this region will be high in that case. So for a free particle, U of R would be a constant. So obviously we would just have the traveling wave solution. There would be no modulation. The psi k of x is delocalized throughout the solid. It's not localized around an atom. It is shared by the crystal. Oh, okay, so we need to prove Bloch's theorem. So psi of x can be expanded in terms of plane waves with all the k values permitted by the boundary conditions. So the sum of any set of solutions of Schrodinger equation is a sum of plane waves, so e to the ikx, sum over k ck e to the ikx, where ck is the coefficient of the plane wave e to the ikx contribution to the solution. So for a cubic sample of edge length L and with periodic boundary conditions, we say that the wave function psi at 0 must be equal to psi at L at the boundaries. So we have e to the ikL equals to 1, k is equal to 2n pi over L, where n is an integer. So since psi of x is defined everywhere in the crystal, k values are not limited to the first Brillouin zone. It's a delocalized way. If you write the Schrodinger's equation taking this form, the wave function expanded into plane waves. So if you write it expanded into plane waves, sum over k ck e to the ikx. This is basically going to give us, for the second derivative, minus h bar square over 2m d squared dx square e to the ikx will give us ik parenthesis square, which is minus k square. So we will have h bar square over 2m k square sum over k square ck e to the ikx. And then we will have, for the potential that's expanded as sum over g vg e to the igx, that's Fourier series expansion, so that will give us e to the ig plus kx sum over k and sum over g. And on the right hand side we have energy times sum over k ck e to the ikx. So this is just Schrodinger's equation where we have substituted for the wave function psi the plane wave expansion sum over k c of k e to the ikx. So the first term, as I said, gives us the k square and minus sign disappears because we have ik parentheses square. And then the second term, sum over j sum over k vg ck e to the ikx e to the igx, and then we have energy times the wave function. So if we transform this from k to k prime, where we define k prime as k plus a reciprocal lattice vector g, then we will have, for the second term, sum over k, g sum over k vg c of k e to the ik plus gx will become sum over k prime. For k, we are substituting k prime minus g, and for k plus g, we are substituting k prime. So k prime is a dummy variable, so we might as well sum over k, so it doesn't matter. So basically this is going to be h bar square over 2m sum over k c of k square e to the ikx plus sum over g sum over k c of k minus g vg e to the ikx, and then here we have energy times the wave function. The reason I have done this is because I wanted to have everything written in terms of the plane wave solutions e to the ikx, because sum over k c to the ikx functions are linearly independent functions. Basically I can write the coefficients on both sides to be equal. So that was the idea. So h bar square k square over 2m c of k plus sum over g c of k minus gvg is equal to e c of k. So what I have done here is basically I got rid of sum over k e to the ikx's. So this is basically the parentheses that I have considered here. So I obtain an equation for the coefficients h bar square k square over 2m minus e c of k plus sum over gvg c of k minus g is equal to 0. This equation that I have obtained here is called the central equation, and what it is it's just a Schrodinger equation for the Fourier components, so in the i.e. the ck's of the wave function psi. So if psi is in the form of sum over k c of k e to the ikx, it says basically you can see that these c of k's are functions of k, so that's one thing I have to consider, and at the same time I have coefficients of the form c of k minus g on the right hand side. So this is a solution of the Schrodinger equation if we as we assumed that not all the wave vectors enter into the Fourier expansion. We find that if one value of k is known to be contained in a particular psi, then other vectors in the expansion must have the form k minus g or k plus g. So that comes from this potential term here, c of k minus g. And we're summing over g, so we have k minus g or k plus g, etc. That has this form. So if we pick 1k, then the set of wave vectors in the Fourier expansion is determined by adding or subtracting reciprocal lattice vectors. For example, in one-dimensional crystal, in k space, the k values would be, if we have one particular k value known, that is k0, then we would have k0 minus 2 pi over a, k0 plus 2 pi over a, etc. So add or subtract reciprocal lattice vectors from the k vector. Okay, so in one dimensions we have a g is equal to 2 pi n over a, where L is equal to capital N times a is our length, so it's capital N times the lattice constant, and we usually label psi with the k value in the first Brillouin zone. So you can see that because when I pick a k value, I have to add to it a reciprocal lattice vector or subtract a reciprocal lattice vector. Psi k will have only one component in the first Brillouin zone. The next component will be outside the Brillouin zone. So the wave function has the form sum over g c of k minus g e to the I k minus gx. So because c of k's are in this form. So it was sum over k c k e to the I k x, but all k's are in the form sum over g c of k minus g e to the k minus gx. So basically, by having this substitution, k becomes k minus g, and instead of summing over k, I'm summing over g. That basically goes through all possible k values. I can write psi k of x as sum over g c of k minus g e to the minus igx e to the ikx. So I define this sum over g c of k minus g e to the minus igx as my function uk of x, so that psi can be written in the form uk of x e to the ikx, which is the Bloch state function. So this is Bloch's theorem. There's one thing remaining. I have to show that uk of x is invariant under lattice translations. So if I write uk of x plus r, sum over gck minus g e to the minus ig x plus r, because e to the minus ig dot r is equal to 1, this is going to give me the same function. So uk of x plus r is equal to uk of x. Therefore, I find that after a translation by a relative position vector r, the wave function acquires a phase factor e to the ik dot r. So psi of x plus r is equal to psi of x times e to the ik dot r. So you can see that psi of x is not periodic. However, if you look at psi of x square, psi k of x square, that is periodic, because the magnitude of e to the ik dot r will be 1. So there's one more thing here. If the potential vanishes, if all these coefficients C of k minus g are equal to 0, except for C of k, the central equation will become, because if you go back to the central equation, these are all in the form C of k minus g. So I can only have k, but there are no k minus g's or k plus g's, so the potential vanishes. So then I'm left with the equation h bar squared k squared over 2m minus e. C of k is equal to 0. So that tells me that the energy must be equal to h bar squared k squared over 2m, and the solutions of the Schrodinger equation are of the form C0 e to the ikx. So that basically boils down to the free electron case. So we check the limit of the free electron case. When we equate the potential to 0, we find that we do recover the free electron solutions. The momentum h bar k is called the crystal momentum of the electron. And when we have collision processes of the electrons in the crystal, for example with phonons, this is going to enter the momentum conservation equations as the momentum of the electron. So in an electron wave vector k collision with a phonon wave vector q, the selection rule for the phonon absorption will be k plus q is equal to k prime plus g. So this g is going to correspond to the lattice recoil momentum. So if you multiply this by h bar, it will correspond to the lattice recoil momentum. So as you can see, we have the momentum conservation equation written using only the k vectors of the electron and the q vector or the wave vector of the phonon, and also reciprocal lattice vectors. Okay, so in summary, we have basically discussed the fact that we cannot use the free electron model to explain all of physical phenomena such as positive Hall coefficients, behavior of semiconductors, etc. And to account for these, we introduced a periodic potential which gave us the bands, which will give us the band structure of a crystal, and we will find that due to Bragg reflections at the zone boundaries and standing wave solutions that form due to the interference of these solutions, we will find energy band gaps at the zone boundaries. Now, when we have a periodic potential, this can be expanded into a Fourier series, sum over GV G e to the IG dot R, just like any physical property of the crystal that is periodic. So if you recall, we had the electron density that was expanded like this into a Fourier series, and the form of the wave function that satisfies this condition is called the Bloch wave function, which has a function of position that is periodic with lattice translation vectors u of r times a plane wave, the traveling wave e to the I k dot r. And these Bloch functions are basically traveling wave solutions that are modulated periodically with this function u of r. It is delocalized throughout the crystal. We prove Bloch's theorem by expanding the wave function psi of x into traveling wave solutions of coefficients c of k. So it's a sum of these traveling wave solutions that satisfies the Schrodinger's equation, and we use periodic boundary conditions so that k is equal to 2n pi over l. When we substitute our plane wave expansion of the periodic of the wave function and the periodic potential, we find the Schrodinger equation for the coefficients of the plane waves, sum over k e to the ikx. That's called the central equation, and central equation tells us that these wave vectors must have the form k minus g, k plus g, etc. So if you know one k value for a wave function, then all the other k values will have the form plus or minus reciprocal lattice vectors. So this central equation, we see that it gives us basically the following result. Because we have all k values written in terms of k minus g or k plus g, we can write the wave function as sum over g c of k minus g e to the I k minus gx. And that basically proves for us the Bloch's theorem, because we identify our modulating function, a sum over g c of k minus g e to the minus igx, which is invariant under lattice translations, and as a result we find that it's not the wave function, but it's the absolute value of the wave function squared that is periodic, which is the probability of finding the electron in a region x at position x. So psi of x squared dx is to find the probability of finding the electron in the region x to x plus dx. And if the potential vanishes, all of these coefficients c of k minus g are 0 except c of k, so we have only the k value but not k minus g's or k plus g's, then that gives us the free electron case and we find the free electron solution. The h bar k is called the crystal momentum of the electron. It enters all the collision processes where we write the momentum conservation as the momentum of the electron, and we have demonstrated if we have an electron-phonon collision, for example, the phonon absorption process will result in the scattered electron wave vector k prime plus the reciprocal lattice vector g that corresponds to the momentum that is transferred to the crystal structure.